So this video is for E1 paper 1A questions, multiple choice questions. And we're starting off with a emission diagram for an atom. You can see, if you look closely, there are two lines and then a double line on the left, and then there's another double line on the right. And I know that E equals HF from the data booklet, so energy and frequency are directly proportional. And since C equals F lambda, energy and wavelength are inversely proportional. So if the wavelength is increasing to the right, that means that energy is increasing to the left. But looking at the answer choices, there really should be a double line on both sides for increasing energy. And there's only one answer choice that has a double line for both low energy and high energy, and that would be choice A. I don't know why they did not include the single lines in that diagram, but of the answer choices, there really has to be a double line for both high energy and low energy, and A is the only one that has that. So that's A. And then for number 2, there are obviously 4 answer choices. It seems that the other 3 are over here. But we have, this gives us the energy of nth level hydrogen is negative E naught over n squared. And that fits because from the data booklet we have the energy of a electron in hydrogen as negative 13.6 EVs per n squared. So E naught would be the negative 13.6. So we're going from level 4 to level 2. Okay, so following this equation where energy is E naught over n squared, we're going from 4 to 2. So the change in energy would be from 2 to 4. And so that's 2 squared. It's pretty much 1 over 2 squared minus 1 over 4 squared. So we get the least common denominator being 16. So it'd be 4 over 16 minus 1 over 16 is 3 over 16. So from the energy transition from 4 to 2, it's going to be 3/16 the energy. But as for the frequency, we know that energy equals HF, so frequency is E naught over H, so it's 3/16 of E naught over H. And so that's, but the answer is broke for some reason, so it's not A, but we go over to these choices here, up here, and we see 3/16 E naught over H. So yes, the answer is B. I don't know if you guys can hear Ed on the video talking about the Super Bowl. Okay, now here's 3. Yeah, I don't know why. Man, they really screwed up the formatting on this. Alright, anyway, let's take a look at number 3. So we have an alpha particle with 5.5 MeV moves towards the center of a nucleus of gold. And what's the distance of closest approach with the alpha particle? So the way this works is the alpha particle is moving towards the nucleus of gold with a certain amount of kinetic energy, but they're both positive, right? They're both positive, so they're repelling each other. So that gold nucleus is repelling the alpha particle. Eventually, the alpha particle slows, and all of its kinetic energy goes to potential energy in the field. Now, we know that the potential energy between two particles in a field, that's from topic D2, that potential energy is KQQ over R. So we know the two different charges, we know the electrostatic constant K, and we want to know what is R. Now we can go back and take a look at the particles up here, and we can get their charges in elementary charges because the energy is in electron volts. However, we're going to have to convert from elementary charges in electron volts to coulombs and joules because we're using the electrostatic constant K, which is given in terms of coulombs, the standard unit for charge, which is what I like to call the big unit, as opposed to the little unit being the elementary charge. So let's take a look at the particles. We have an alpha particle, which is 2 elementary charges, plus 2, and which turns out to be 3.2 times 10 to the negative 19 coulombs. And our gold nucleus, which is plus 79, which is 1.264 times 10 to the negative 17 coulombs. Then we have 5.5 mega electron volts, and that turns out to be 8.8 times 10 to the negative 13 joules. for the energy. So we'll put all these numbers into our formula down here and get an answer. Electrostatic constant K from the data booklet is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Throw all of our numbers in there, and we get 4.1 times 10 to the negative 14 meters, which is B. Now we have number 4. It says alpha particle scattering experiments carried out with the high energy alpha particles. Deviations from the Geiger, Mars, and Rutherford scattering were observed. And there's like, what was deduced as a result of this observation? The size of the alpha particle, the size of the nucleus, nature of the electrostatic field inside the nucleus, and the nature of the weak nuclear force within the nucleus. No, they didn't probe the nucleus itself, but it was the effect of the nucleus on the alpha particles. So remember that they, most of the alpha particles that went towards that gold foil went through the gold foil, meaning that the gold was mostly empty space. But by probing the foil itself, by looking at the scattering pattern, they could figure out how big the nucleus was. And so as they're shooting alpha particles towards the nucleus, most of those alpha particles are going straight through. But for the ones that did hit the nucleus, they were scattered away from the nucleus. Some of them went right back towards the source, some of them scattered off at angles, but based on the angles that they were scattering at, they were able to figure out exactly how big that nucleus was. So yeah, what they figured out was the size of that nucleus. Oh, number 5 is pretty basic. Energy levels of an atom. Which transition results in the emission of an electron with the shortest wavelength? Well, we know that E equals hf and C equals f lambda, so therefore energy of a photon is hc over lambda. So energy and wavelength are inversely proportional. So if we wanted the shortest, the smallest wavelength, that would be the most energy, and so it would be the biggest gap of the bunch to give it the most energy, and so that's going to be D. So to do number 6, you first have to realize what angular momentum is. And angular momentum, L, is mvr. And it was like, well, if you go back to, what was it, A4? Is it A4? Let me scroll back here. A4, yeah, rigid body mechanics. We know that angular momentum is moment of inertia times angular velocity. So let me just show you like this kind of derivation. So from A4, we know that angular momentum is moments of inertia times the angular velocity. We also know that moment of inertia is sigma, the sum of the mr squares. But it's like, well, if it's mr squared, why does L equal to mvr? All right, well, bear with me. We know from SHM that angular velocity is 2 pi times, angular frequency is 2 pi times the regular frequency. It's also equal to 2 pi over the period. So if I sub that in, I get L is mr squared 2 pi over the period. And so if I pull out one of the r's, I get r over t and I know that the distance or the circumference is 2 pi r, so that becomes m d over t r, and v equals d over t, so we get L equals mvr. I think that's a bit much. I feel like they should put that on the data booklet, but they didn't, so there's like the derivation. Like, I feel like that's one of the things that you may need to be aware of. And it's like, well, that's cute, like, why do we care about that now? Because when we talk about angular momentum of first excited state over angular momentum of ground state, they're talking about mvr. Now, why do I care about that? Because we have from the data booklet for E1 that mvr equals 2h nh over 2 pi. And so we're talking about the first excited state over the ground state. Ground state n is 1. First excited state n is 2. And so we have 2h over 2 pi over 1h over 2 pi. And then the h's cancel and the 2 pi's cancel. And I wind up with 2 over 1, which is the answer, choice 2. Or choice C, the answer is 2. So I think the math on that was easy, but realizing that mvr is angular momentum, I think, is the key to that question. that's, I would say, more like rigid bodies and simple harmonic motion than than an E1 question, honestly. But that was number 6. Okay, number 7, we have more Rutherford, Geiger, Marsden, Rutherford scattering. So the Geiger-Marsden scattering, we know that it's 2 allows for an estimation for the radius of the nucleus, because most of the alpha particles scattered at small angles or went straight on through, but a bunch of the alpha particles did bounce off of the radius, and so based on the alpha particles, a lot of them went straight on through, but some scattered at small angles, some scattered back. But based on that scatter pattern, you could figure out the size of the radius of the nucleus, but also the fact that the alpha particles were not able to split the nuclei of the gold, foil, the gold nuclei themselves. It showed how the nuclei kind of holds itself together. And the scattering does not have to happen at low energies, but it did provide for the evidence of the strong force, but especially number 2. So it's really 1 and 2 only, and that would be A. And the answer actually is all the way over over here. Love the way it's splitting this up, but yeah. So A, 1 and 2. Okay, let's go over to number 8 now. And number 8 is a repeat. We actually saw number 8. It is literally the same as number 5. Thanks a lot, QBank. So then forget number 8. And looks like number 9 is a repeat. Number 10 is a repeat. Number 11 is not a repeat. All right, so then let's see. We're going to get rid of 8 because that's a repeat. Number 9 is a repeat. Number 10 is a repeat. And then 11. Okay, so 11 starts here and then continues over there. Let's take a look at number 11. And this is Bohr model for hydrogen. Radius of the electron orbit in the n equals 2 state is 4 times that of the radius in the n equals 1 state. Okay, noted. And then what they're asking over here is what is the speed in the 2 state over the speed in the 1 state? That's what they're asking. All right, so let's see. I know that for the angular momentum equation, we have mvr equals nh over 2 pi. And so speed is going to be nh over 2 pi mr. And so if we divide up the speeds v2 over v1, we get for the second level, that's 2h over 2 pi m 4r, because it said that the radius of 2 is 4 times the radius of 1. And then the velocity at n equals 1 is going to be 1h over 2 pi m regular old r. So let's start breaking this down. And when you start canceling things out, you basically get 2 over 4 over 1, which is 2 over 4, which is 1/2. So the ratio of the speed of the n equals 2 electron to the speed of the n equals 1 electron would be 1 over 2, which the answers are over here, 1 over 2, which is B. So yes, that's true. There you go. All right. Let's see. Number 12. Variation of nuclear density rho with nucleon number A. Ooh, that was in the notes. That's a great... Oh, there's a graph. Man, this formatting is a hot mess. Okay. So what is the variation of nuclear density with nucleon number? Well, density is mass over volume. All right, so we have density is mass over volume. Volume of a sphere is 4/3 pi r cubed. the radius of the nucleus is r naught a to the 1/3. That's from the data booklet. And so I throw in r into the volume equation, and I get that volume is 4/3 pi r naught Fermi radius cubed times the nucleon number. And then the mass in mass per unit volume is the mass of a nucleon, proton, or neutron times the number there are, times the nucleon number for that nucleus. Because if it's whatever the nucleus might be, however many protons and neutrons you have, it's that mass of 1 times the number you have. But that that nucleon number is in the numerator, but it's also in the denominator, and so they cancel. And so there's no relationship between density and nucleon number, or in other words, the density is the same for all nuclei. The density of the protons and neutrons, which is kind of neat. But that means that of the graphs, there is no relationship, and so it's B. Okay. Number 13. Do we have answer choices for 13? Somewhere? Maybe they're over here? Yes. Okay. Let's go with number 13. So the energy of a level of hydrogen, of the electron in a level of hydrogen, is negative 13.6 eV over n squared. So I put the energies for levels 1, 2, and 3 being negative 13.6 EVs over 9, 4, and 1 for 3, 2, and 1 respectively. Okay, so now that I have the energies for each of the levels, we have transitions for y going from 3 to 1 and for x going from 2 to 1. So I solve for the change in energy by just doing a simple final minus initial, final level minus initial level, paying close attention to the negatives. So I have, for the transition from 3 to 1, I have, again, final minus initial, so 1 minus 3, so negative 13.6 over 1 minus negative 13.6 over 9, getting me negative 12.0889 EVs. And then from 2 to 1 to the same thing, I got negative 10.2 EVs. Technically, the convention is that emitted photons are positive energy, absorbed photons are negative energy, but whatever. It's not going to matter anyway because we're doing a ratio, right? But it's asking about the wavelength, not the energy. So we know that E equals hc over lambda, therefore lambda is hc over E. So it said wavelength for x over wavelength for y, so it would be hc over the energy for x divided by hc over the energy for y. The hc's cancel, and so I have energy for y over energy for x. So that would be negative 12.0889 EVs divided by negative 10.2 EVs, and that's a ratio of 1.19. So then I go check my answer choices over here, see what the ratios are, if I can actually find them. Here they are. And so like I said, I'm looking for 1.19. It is definitely not 2. It is definitely not 1/2. And I'm looking for something greater than 1, so it's not 27 over 32. It must be 32 over 27. And lo and behold, it is. So 14 is interesting. It says there are 3 equations, and it says which ones refer to the Bohr model for hydrogen. Well, why don't you check your data booklet? And so we have the E equals negative 13.6 over n squared EV. That's the energy of the electron per level. We just used that in number 13. So yes, that is for the Bohr model for hydrogen. And then we have 3 there is the angular momentum, MVR, the quantization of angular momentum based on the level, nh over 2 pi. So whatever your level is, it varies by h over 2 pi. Yes, that does refer to the Bohr model. But the second guy we haven't gotten to yet, that's for radioactive decay. And n refer to the number of nuclei, and so yeah, that's an exponential decay there. And that is not for hydrogen, that's for everything radioactive. And so not 2. And so it's just 1 and 3, B, which agrees with the mark scheme, which is actually over here because reasons. And then 15, we're going to skip 15 but it says which emission shows a continuous energy spectrum. And actually, the wrong answer, A, is relevant to the topic at hand. Photons during energy transitions between atomic energy states is not continuous, it's discrete. That's the evidence of the quantization of the energy, so it's definitely not choice A. But the other answer choices deal with radioactive isotopes. That is not topic 8, topic E1. Radioactive isotopes is topic E3, which is not relevant to E1, so we're going to skip number 15. All right, we're going to number 16. So, hydrogen 2 is a radius r, density rho, approximate radius and density of a nucleus of oxygen 16. Well, we know that all the nuclei have the same density. We saw that in number 12, where there's no relationship between density and atomic number or nucleon number, and so density is the same for all nuclei. So that gets rid of B and D. But what about the oxygen 16 radius? Well, we have an equation for radius. Now we have to read carefully because it talks about hydrogen 2, not regular old hydrogen. So hydrogen 2 has an atomic number of 2. So for H2, hydrogen 2, the radius is about 1.25 r naught. And so for oxygen, which is coming in at 16, that has a radius of 2.51984 r naught. So looking at the two numbers, the oxygen at 2.5 is double the hydrogen at 1.25, giving us A for our answer, and of course they put the answer over here because they're crazy. But that's how you do it. All right, we are getting close to the end. 17. 17 is pretty easy. It says X is a nucleon number AX and nuclear density rho X. Y is a nuclear number of 2AX. What's the nuclear density of element Y? The same, rho X, because all nuclear densities are the same. Giddy up. 18. 18 says diameter of a nucleus of a particular nuclide X is 12 femtometers. What is the nucleon number of X? So the radius of the nucleus is r naught, a to the 1/3. And this talks about diameter, so double the radius is double the Fermi radius times the 1/3 power of the nucleon number. Fermi radius is given in the data booklet. So we put in a 12 femtometers. Femto, of course, means 10 to the negative 15. And we put in 2 times the Fermi radius times a to the 1/3, solve for A. All right, and if we solve for A, that would be 5 to the 3rd, which is 125, which is C. And of course, the mark scheme puts C over here because reasons. And then we have 19, I believe, is the last question. So let's see. Orbital radius. So these are the relationships for orbital radius, quantized energy, and quantized angular momentum. Just be careful with R. The R equals R naught, a to the 1/3 is the radius of the nucleus, not the orbital radius of the electron. But orbital radius of the electron is in R, in MVR equals NH over 2 pi. And so R is NH over 2 pi MV. Energy is quantized in amounts of 13.6 electron volts. You can see that in that equation. It's from the data booklet. And then angular momentum, we've talked about that, about MVR is angular momentum, is also quantized. There's NH over 2 pi. So which of these are features of the Bohr model for hydrogen? Actually, all of them, 1, 2, and 3, and so the mark scheme says D. And that's correct. Okay. So that's 19 problems, sort of, but not really. Like, we have some repeats, so we don't need to worry about those. And that is it for the paper 1As for E1. Thank you.